Today, we'll learn how to solve quadratic inequalities. These are inequalities involving a quadratic expression, like a x squared plus bx plus c is greater than 0, less than 0, greater than or equal to 0, or less than or equal to 0. Let's work through an example. Suppose we want to solve x squared minus 3x minus 4 is greater than 0. The first step is to make sure all terms are on one side of the inequality, with 0 on the other side. Our example is already in this form. Step 2 is to solve the corresponding quadratic equation. That is, we replace the inequality sign with an equals sign and solve for x. So, we solve x squared minus 3x minus 4 equals 0. We can solve this by factoring. We look for two numbers that multiply to -4 and add to -3. These numbers are -4 and +1. So, the equation factors as x minus 4 times x plus 1 equals 0. This gives us the roots or critical points, x equals 4 and x equals -1. Step 3 is to draw a number line and mark these roots on it. Here's our number line. We mark -1 and 4. These roots divide the number line into 3 intervals, from -∞ to -1, from -1 to 4, and from 4 to +∞. Step 4 is to test a point from each interval in the original quadratic expression, x squared minus 3x minus 4, to see if the result is positive or negative. Let's test the first interval, -∞ to -1. We can pick x equals -2. Plugging this in gives -2 squared minus 3 times -2 minus 4, which is 4 plus 6 minus 4, equaling 6. Since 6 is positive, the expression is positive in this interval. Now let's test the second interval, -1 to 4. Let's pick x equals 0. Plugging this in gives 0 squared minus 3 times 0 minus 4, which is -4. Since -4 is negative, the expression is negative in this interval. Finally, let's test the third interval, 4 to infinity. Let's pick x equals 5. Plugging this in gives 5 squared minus 3 times 5 minus 4, which is 25 minus 15 minus 4, equaling 6. Since 6 is positive, the expression is positive in this interval. Step 5 is to write the solution set. Our original inequality was x squared minus 3x minus 4 is greater than 0. This means we are looking for the intervals where the expression is positive. Looking at our number line, the expression is positive in the intervals from -∞ to -1 and from 4 to +∞. Since the inequality is strictly greater than 0, we do not include the roots themselves. So the solution is the union of these two intervals, -∞ to -1, union 4 to +∞. We can also visualize this by graphing the parabola y equals x squared minus 3x minus 4. The inequality asks where the parabola is above the x-axis, since it's greater than 0. As you can see, the graph is above the x-axis for x values less than -1, and for x values greater than 4, which matches our solution. So, to solve a quadratic inequality, remember these steps. Rewrite the inequality, solve the corresponding equation to find the roots, use the roots to divide the number line into intervals, test each interval, and finally, write the solution set based on whether the inequality requires positive or negative values. In this video, we'll solve the inequality x plus 5 times x minus 2 is greater than 3x plus 6. First, let's expand the left side of the inequality. We multiply the binomials using the FOIL method. First terms, outer terms, inner terms, and last terms. X times x is x squared. X times -2 is -2x. 5 times x is positive 5x. And 5 times -2 is -10. Combining the middle terms, -2x plus 5x gives positive 3x. So, the left side expands to x squared plus 3x minus 10. Now, we want to move all terms to one side of the inequality to set it to 0. We subtract 3x and subtract 6 from both sides. Notice that the 3x terms cancel out. X squared plus 3x minus 3x minus 10 minus 6 is greater than 0. This simplifies to x squared minus 16 is greater than 0. Next, we factor the quadratic expression. X squared minus 16 is a difference of squares, which factors into x minus 4 times x plus 4. So our inequality becomes x minus 4 times x plus 4 is greater than 0. To solve this inequality, we need to find the values of x for which the product of the two factors is positive. The critical points are the values where the expression equals 0, which are x equals 4 and x equals negative 4. Let's visualize this on a number line. We mark negative 4 and 4. These points divide the number line into three intervals x less than negative 4, x between negative 4 and 4, and x greater than 4. We need to test where the expression x minus 4 times x plus 4 is positive. Let's analyze the signs. When x is less than negative 4, say x equals negative 5, both x minus 4 and x plus 4 are negative. A negative times a negative is positive. When x is between negative 4 and 4, say x equals 0. X minus 4 is negative and x plus 4 is positive. A negative times a positive is negative. When x is greater than 4, say x equals 5. Both x minus 4 and x plus 4 are positive. A positive times a positive is positive. We want the expression to be greater than 0, so we are interested in the intervals where the product is positive. Therefore, the inequality holds true when x is less than negative 4 or when x is greater than 4. This is our final solution. In summary, we expanded the inequality, simplified it, factored the quadratic expression, found the critical points, and used a number line to determine the intervals that satisfy the inequality.